and 55 gallons are 30 drums per hour. We get, this is 30 times 2.85, and that is 6.24, say. Cubic meters, okay, I did some, per hour. This was actually, this is in this meter. Okay, so that's why it's a fast in order of converting that to cubic meters. Okay, so our RFVC is then 0.014 cubic meters per minute. Our saturation pressure was given in millimeter mercury, and 0.6 millimeter mercury is 79.98 pascals. Saturation pressure, that's ambient. QV was 3,000 cubic feet per minute, I believe. Is that minute, right? And that is equal to 8496 cubic meters per minute. What else do we need? So we've got these. We need K, and we need K, area we have. So we have to calculate K from K0, 1 forward, it's N of to the power third, and K0 is 0.83. 83 centimeters per second. So our K is 18.0152. Okay, and then we need the molecular weight of 2-butoxyethanol. Okay, so the first thing, you could get this problem like this, go to the back of your book. In one of the tables, can't remember if it's the one that has the time-weighted average numbers or if the flammability one has molecular weights. Okay, so if we don't have molecular weight, 2-butoxyethanol, 1, 2, 3, 4, OH. Okay, so that means we have 6 times 12 carbons plus 14 hydrogens and 2 oxygens. So this is somewhat approximated, but our K then is equal to 0.443 centimeters per second, or centimeters, decimeters, meters, the other way, 4.43 10 to the negative 4 meters per second. Okay, so let me write this, all these numbers under here. This is the equation we're using. Oh, I need to write some more. Okay, so our KCPEN. Are you with me on the molecular weight? So the molecular weight is actually 118.18, that's grams per mole. Okay, so I just added the carbons, hydrogen, and oxygens of the components. Okay, so we have PSAT is 79.98 pascals. over QV, which was 84.96 cubic meters per minute times 101.3 pascals. Okay. What are we doing? Subsurface splash filling? Yes, thank you. So I need a 10 to the 3 here. Okay, what's our theta? 1, because we have splash filling. So it is 1 times our 0.104, this is cubic meters per minute, plus our Ka, which is 4.43, 10 to the minus 4. Oops. 4, that's meters per second, times our area, which was 8 centimeters squared, so it's 8 times 10 to the negative 4 meters squared.
Just backtracking a bit, it was 0.014 or 0.104?
I think it was 0.104. I just erased it.
Yeah, that's what I'm gonna make sure I didn't write
Sorry,
it.
yeah, it was 0.104.
Hey,
Would you
what
quick,
What is M naught again? So when you're finding the K?
the K, what did you say, M naught, so this is the molecular weight of this reference. And this is the number for water.
So
So
you just use water.
0.83, so 18, so you whatever, 18 grams per mole is the molecular weight of water. Yes,
Is 0.443 centimeters per second, shouldn't that be 10 to the negative third?
yes,
Centimeters to 10 to the
yes,
negative second.
thank you. That is, it's supposed to be a 3 here. This one, this one is 4 though. Okay, so you quickly realize, right, that in this case in particular, but it could depend on the area, the evaporation term is much, much lower than the filling term. So, which is normally the case if you have a high filling rate and a small area, right, that you're filling through. Okay, so our K, CPPM in this case is equal to 0.968 ppm. Okay, so here's why I wanted this up still. Question, yes?
So I know you said the evaporation rate is small in comparison, but wouldn't we also need to times it by 60 to make it per minute instead of per second?
Oh, yeah, yes, thank you. Oops, it would be nice if I actually followed my, my notes. So K is equal to 0.2658. That's meters per minute. Okay, don't do what I did, what I just did, okay. So, this is supposed to be in meters per second, and it is 0.2658. Okay, so those are the actual numbers, right, that gives this number, okay? Just not looking at my notes, it's just
And then it's all times 10 to the 6. Right?
and then it is all times, so this here, let's put the 10 to the 6 here. Otherwise, you will not get that number.
So the 0.2658 is meters per minute?
This is meters per minute now, yes, I changed this, so it's now correct. So it's still low, right, compared to that. But it's not always. So, right, on an exam, I don't want you to just disregard the evaporation rate without actually checking that it's much lower than the filling rate. Okay, so now we have this dilemma here, right? We have this K that we need to determine. And it's dependent on, so we have to go into this table, it's dependent on the concentration, and then it's dependent on the ventilation condition actually. So whether we have poor ventilation or excellent. And in this case, the QV at 3,000, that's a pretty good ventilation rate. So we're probably over on this end, right? And then, so what we have to do is look, what is K? If you look at the K numbers, the K values, they go between 1/11, so 0.1 roughly, to 0.5. So in other words, this concentration would go between 10 times this, 9.68, to about 2 times this. Okay, are you with me? In terms of, regardless of these, the numbers for K, if you go across the whole table, only go from 0.1, say, roughly to 0.5. In other words, if we look at the concentration here, we're never gonna be over 500, we're never gonna be over 100. So regardless, we're at the low concentration region, which means because of that, our K factor is gonna be between 1/11 times 1, or between 1/11 or 1/6. And if we go back to the actual problem, it doesn't really say what the ventilation rate is or what ventilation quality is. So if it's not mentioned, right, going in here and saying, I assume that it's about average would be okay.
For
At
sure.
3,000 cubic feet per minute, you're probably in the good to excellent rate, quality. But, right, if you're on an exam, it would be stated. But if it's stated, right, I do not want a range of K values. If I state that the ventilation quality is good, then that's the number I want you to use. So I know that you know where it comes from. So in this case, let's assume good quality ventilation. That gives us that our K is good quality, low vapor phase, it's 1/7. Which means that our concentration is, let me hope I actually put the number somewhere. Because someone multiplied this by 7.
6.7.
6 points, say it again, 6.78.
78.
Okay, I had actually just looked at what the difference is. At low concentrations, if K is 1/11, you get a CPPM of 10.6. And if you have an excellent quality ventilation, you get a CPPM of 5.8. But I'm wary about putting a range on here, because then I'll always get students who put ranges on the actual exam. Even though in this case, we weren't given the ventilation rate, so it would be between those two numbers. But, right, on an exam, you would specifically be given something. Okay, I took a little more time than I should have. Any questions? We'll continue next week.